Hi friends, good morning respected ma'am, good morning all of you. Myself Rituja Ambekar, roll number 2, and my seminar topic is the selection of drug candidates and the approaches to design a controlled release formulation based on a diffusion and a dissolution. In this my seminar, we are going to complete the points that are the factors affecting for the selection of the drug candidates and the types and the examples for the approaches to design a controlled release formulation based on a dissolution and a diffusion. First, we see that the selection of the drug candidates. There are different factors are used for the selection of the drug candidates. First is the physicochemical factor, biological factor, and the pharmacodynamic factor. Let's see it one by one. Physicochemical factor. In this, first one is the aqueous solubility. Low solubility drugs are poor candidates for the controlled release drug delivery system. Means the low soluble drugs are the poor criteria for the selection of the drug candidates. Solubility should be pH independent. Drug should have a minimum 0.1 milligram per ml. In the aqueous solubility, compound with the very low aqueous solubility usually suffer oral bioavailability problems because of the limited solubility at the absorption site. For example is the glycerofluin. Second is the molecular weight of the drug. Ability of the drug to diffuse through the membrane is known as a diffusivity, and diffusivity is inversely proportional to the molecular weight. 90% of drugs are absorbed by a passive diffusion. The lower molecular weight can faster and more complete the absorption from drugs absorbed by a poor transport mechanisms. Hence, the lower molecular size of drugs are a good candidate for the controlled release drug delivery system. Hence, the drug with the large molecular size are poor candidates for the controlled release drug delivery system. For example, is the peptides and the proteins. Third is the partition coefficient of the drug. Partition coefficient is defined as the concentration of unionized drug is distributed between two phases at equilibrium. It can be given by the Noyes and the Witness equation. Partition coefficient influences not only the permeation of the drug across biological membrane but also diffusion across through the rate controlling membrane or the matrix. Here is the diagram of the partition coefficient of the drug. Fourth is the ionization at a physiological pH. Drug existing largely in ionized forms are a poor candidate for the controlled release drug delivery system. For example is the hexamethonium. Fifth one is the drug stability. The stability of the drug in the environment to which it is exposed is another physicochemical factor to be considered in the design of the controlled release drug delivery system. Drug unstable in the GI environment cannot be administered at the controlled release drug delivery system because of bioavailability problems. For example is the nitroglycerin. Next factor is the biological factor. In this, first one is the absorption. Absorption is important to maintain the constant blood or tissue level of drugs. Absorption efficiency differs throughout the GIT, which directly affect the extent of a drug absorption from the site. Most of the drugs are poorly soluble and poorly permeable, thus they are less absorbable. Thus, in such cases, the use of a controlled release drug delivery system enable them to carry out into the cell easily. The drug with the slow absorption is a poor candidate for the selection of the drugs. For example is the iron. Next is the metabolism. Metabolism of drug can convert an active drug into inactive or inactive drug to the active. Metabolism to other active form can also be considered as a sustained effect. The extent of metabolism should be identical and predictable when the drug is administered by a different route. Drugs with the rapid metabolisms are not suitable. Next is the biological half-life. It plays a major role in the selection of the candidates. Factors influencing the biological half-life of drugs includes its metabolism, elimination, and the distribution. Very low and very long half-life is not a good candidate. It should be in optimum inner range. More than 8 hours are also generally not used in sustaining forms since their effect is already sustained. For example is the warfarin, digoxin, etc. Next factor is the pharmacodynamic factor. in this therapeutic index. A candidate for a drug of the CRDDS should have a high therapeutic index so that variation in the release rate do not result in a concentration beyond this level. This is necessary because narrow therapeutic index drugs are having toxic concentration nearer to their therapeutic range. Here we completed the factors affecting for the selection of the candidates. Next is the approaches to design a controlled release formulation based on the diffusion and the dissolution. For a drug to be successfully as a controlled release drug delivery system, it must get absorbed through the entire length of the GIT. Oral route has been most popular and successfully used for a controlled delivery of the drug because of convenience and ease of the administration, greater flexibility in dosage form designs, and ease of the production and low cost of a such system. In this, first we see that the dissolution controlled release system. This system is easy to design. The drug with the slow dissolution rate is inherently controlled or sustained by this system. This dissolution process, steady state, is described by the noise and the Witness equation. That is, dc divided by dt is equal to kdA in bracket cs minus c bracket close is equal to d divided by h in bracket cs minus c, where is the dc by dt is the dissolution rate, Kd means the dissolution rate constant, D is the diffusion coefficient, Cs means the saturation solubility of the solid, C is the concentration of the solute in the bulk solution, and A is the surface area. In this diagram, we can see that the polymer membranes with the different dissolution rate. Here are the two types of the dissolution system. First one is the reservoir dissolution control and the second is the matrix dissolution control. Here is the formulation are made in such a way that it can decreases the rate of dissolution of the drug. The rate approaches to achieve this include preparing appropriate salts or derivatives, coating of the drug with the slowly dissolving material, or incorporating it into tablet with the slowly dissolving carrier. Here is a classification of the dissolution controlled system. First is the matrix dissolution controlled release system and the second is the encapsulation dissolution controlled release system. First we see that the matrix dissolution controlled release system. Matrix dissolution devices are prepared by the compressing the drug with the slowly dissolution carrier into the tablet. In this system, the drug is homogeneously dispersed throughout the rate controlling medium. The waxes are used for such systems are bees waxes, carnauba wax, hydrogenated castor oil, etc. These waxes control the drug's dissolution by controlling the rate of the dissolution fluid. Here is a diagram of the matrix dissolution controlled release system. In this diagram, by increasing the time, drug is dispersed uniformly in a non-degradable matrix. Second type is the encapsulation dissolution controlled release system. Encapsulation involves coating of individual particles or granules of a drug with a slowly dissolving material. The particle obtained from after coating can be compressed directly. Dissolution rate of a coat depend upon the solubility and the thickness coating, which may range in a 1 to 200 pi, called as a coating dissolution controlled system. In this diagram, we can see that the slowly dissolving or erodible coat of the drugs. Next is the diffusion controlled release system. In this system, rate controlling step is not dissolution rate but the diffusion of dissolved rate through the polymeric barrier. This system is a halo containing an inner core of a drug. The water insoluble polymeric material surrounds the drug's reservoir. The process of diffusion generally described by the Fick's first law. That is the J is equal to minus D into dC upon dx, where is the J means the flux and D is equal to diffusion coefficient of drug in a membrane, and the dC upon dx is the rate of change in the concentration. The drug release rate is never zero order since the diffusional path length increases with the time as the insoluble matrix is gradually depleted of the drugs. There are also two types of the diffusion control release system. First is the matrix diffusion controlled system, and the second is the reservoir diffusion controlled system. First, we see that the matrix diffusion controlled system. As the name implies, it consists of the drug dispersed homogeneously throughout a polymer matrix. The rate controlling element is either a water soluble material such as xanthan gum, guar gum, hydroxypropyl methyl cellulose. There are also two types of the matrix diffusion control system. First one is the soluble matrix diffusion control system. It is also called as the glassy hydroxy gels. And the second is the rigid matrix diffusion control system. The materials used in this are the plastics such as the PVP and the fatty acids. Second type is the reservoir diffusion controlled system. In this system, the rate controlling element is a non-soluble, water-insoluble polymer. For example is the ethyl cellulose. It controls drug release through the micropore. It is characterized by the core of the drug, the reservoir surrounded by a polymeric membrane. The nature of a membrane determines the rate of release of a drug from the system. For example is the hydroxypropyl cellulose and the ethyl cellulose. In this the reservoir diffusion control system diagram, we can see that the polymeric content in a coating and the thickness of the coating and the hardness of the microcapsules. Here we completed that the selection of the drug candidates factors and the approaches to design a controlled release system based on diffusion and dissolution. Hope you understand it carefully. Thank you.